Now in this video, we're going to be talking on Kolbe'S electrolysis method in alkane preparation and total synthesis method in alkane preparation. Now, Kolbe'S electrolysis method. Now this involves the electrolysis of sodium acetate or sodium alkanoids to yield an alkane. It is used in the preparation of higher alkanes, and the mechanism of this reaction is a free radical mechanism. Since it involves electrolysis, it also involves the migration of ions to the cathode and to the anode. Now, general equation of the reaction is given below. We can see that 2 moles of sodium acetate react with 2 moles of water to yield an alkane and to yield carbon dioxide, 2 moles of carbon dioxide, and to yield hydrogen gas. Now, what's actually going to happen is that we all know electrolysis, before it occurs, like ions need to actually split into their respective like cations and anions. Let me just put it that way. So we can have something like RCOO, and it will actually split to the acetate ion and the sodium ion. Now the acetate ion is actually going to migrate to the anode, and the sodium ion is actually going to migrate to the cathode. Now at the anode, let's start with the acetate. Let's start with the acetate ion. That's the most important ion here because that ion will actually yield our alkane. So at the anode, what's actually going to happen is that 2 moles of this acetate ion is actually going to lose 2 electrons, and it's going to lose 2 electrons and it's going to form an acetate radical. Now this radical, 2 moles of it, these 2 moles of this acetate radical is actually an unstable radical, and it's actually going to decompose. It's actually going to decompose to give us our alkane. This is like a general equation. I'm going to actually give us like the mechanism and carbon dioxide. Now this is just like general equation. So let's go to the mechanism of this reaction. Now this is the structure of the alkane, or this structure of the acetate ion. This structure, like I said, 2 moles is needed. So 2 moles of this is actually going to gain 2 electrons. And when it gains these 2 electrons, it's going to yield to the formation of a radical here. And this radical that is actually going to be formed is the acetate radical. And that's this in general. This is the acetate radical. And 2 moles of it is actually going to be formed. From our equation, we can actually see that. Now, what's actually going to happen here? Let me just take 1 mole first. Then, from that 1 mole, we can actually decide what is going to happen to the 2 moles, and we can actually finish everything immediately. Now, we have something like this. Now, like the radical is already formed. Now, what's going to happen here is that the bond between this alkyl group and the acet and the carboxylic group is actually going to fuse or break homolytically, and so what's going to happen is that electrons is actually going to be like transferred to each pair, like single electron, and that's going to yield to the formation of an alkyl radical and a carboxylic radical. And let me just take this up and show you like a full demonstration of it. So I'm going to have something like this. Like I said, the bond is actually going to break homolytically. So now the ions migrate here, and it will lead to the formation of an alkyl radical and a carboxylic radical, and this is a double bonded with O, this single bonded with O. There's a radical here, and now this is actually what's going to be formed. So before I focus on the alkyl radical, let me focus on the carboxylic radical, and let me show you how it's going to use the formation of carbon dioxide. Now this is the carboxylic radical. What's going to happen at first is that this radical at the top of the carbon ion is actually going to move down here, and this other radical at the top of oxygen ion is actually going to move down here to this bond between the carbon and the oxygen atom and the oxygen radical atom, and that will yield to the formation of a bond, and that bond is actually going to combine this carbon and this oxygen, so we can have something like this going to be formed. This is not the real shape. I'm actually going to draw the real shape. Now, if we look at this molecule is a carbon dioxide molecule, and the shape of it is linear, and this is what we're actually going to have. This is what's actually going to be formed. The mechanism is not hard. All you just need is that after you form a radical, you observe that radicals are unstable. We all know radicals are unstable. So in order to annul this instability, they're actually going to migrate. Like the radical is actually going to, instead of it looking for which is easier for it, if we can actually use our brain and decode this, which is easier to look for molecules to combine with and form a larger complex, or just to, since you have a partner that you're already bonded with that have a radical, it's easier for those two radicals to actually combine and form a bond, and that bond is going to lead to the formation of a carbon dioxide. Now, like I said, when I do for one, you can understand for two. So I can say 2 moles will lead to the formation of 2 moles, and at the end, you have 2 moles of carbon dioxide formed. Now, let's talk about the alkyl radical. I say that's the most important. I said 2 moles of the alkyl radical is actually going to be formed. So we have something like 2 moles of this alkyl radical formed. And what's actually going to happen is that this radical, they're going to combine individually. Now, like the same thing, instead of them looking for another radical to combine with to form a bond, you have another radical close to you, that's like a partner to you. So what's actually going to happen is that these 2 radicals, they are going to combine together, and they are going to yield to the formation of a bond, and that bond is going to be formed between the 2 alkanes, and that's actually what's going to happen at the anode. Now let's go over to the cathode. Now, a cathode, this is not really important, but let me just talk about it since I'm talking about the entire reaction. Now, a cathode, what's going to happen? Like I said, sodium ion will migrate to the cathode, and it's going to be discharged. It's going to actually gain 2 electrons, and it's going to turn to sodium metal, 2 moles of sodium metal. Now, these 2 moles of sodium metal, now let's just go over to basic chemistry, or what should I say, basic physical chemistry. When sodium is added in water, what's actually going to be formed? Sodium hydroxide. We all know the reaction is like, let me just put it, it's so reactive that it's going to yield to the formation of sodium metal immediately. That's why we normally store sodium under paraffin, or in order to prevent oxidation by atmospheric oxygen, or even by moisture in the air that will actually yield. And this reaction is actually an explosive reaction. So we all know about this. So we can now say 2 moles of this sodium is actually going to combine with water, and this is going to yield to the formation of Na plus hydrogen gas is actually going to be involved in the process. So it's not balanced, so I can have 2 moles here and 2 moles here. Now the equation is balanced. Now this is all about the Kolbe'S electrolysis method of preparing alkanes. Now the last method I'm actually going to talk about is total synthesis method of preparing alkanes. Now, this method is not actually a complex method. It's not actually even used in preparing, because it's only used to prepare lower alkanes. Lower alkanes. As we go further, like down the homologous series, we're going to find out that this reaction ends up not becoming feasible at all. So now, this method involves the reaction of constituent elements to produce the resulting alkane compound. It's mainly used in the preparation of lower alkanes, as on getting higher in the homologous series, the reaction becomes unsuitable and unstable. Now, lower alkanes such as methane, ethane can be prepared. There's a H here, sorry. Lower alkanes such as methane, ethane can be prepared by discharging an electric arc in between carbon electrodes at a temperature of 120 degrees Celsius in atmospheric hydrogen. Now, as we can see, just to prepare lower alkanes, look at the temperature needed. Now, imagine us going down the group, how much we can require, like 10,000 and so on. And that temperature is even higher than the temperature of the surface of the sun. So what the hell? And we're trying to actually be economical in the preparation of all of this. So it's actually used in preparation of methane and ethane. And this method might not actually be needed, because we all know natural gas is actually the best method of preparing methane and ethane because it can be obtained there freely. But we also can use this method to by discourage this method. Now, like I said, lower alkanes such as methane, ethane can be prepared by discharging an electric arc in between carbon electrode at 120 degrees Celsius in atmospheric oxygen. Now, these are the equations of the reaction. 1 mole of carbon combined with 2 moles of hydrogen gas to yield to the formation of and methane, 2 moles of carbon combined with 3 moles of hydrogen gas to yield the formation of ethane, and so on. So that's all. Thank you for viewing. Please like and subscribe to my channel. Thank you.